Good morning, student. Glad to have you in my class.
Good morning, Math Qube. I'm excited for today's class on time shifting. Can you give an example before you go on math cubing on me?
Of course, let's see an example. Let's take this example. When you go to movies, you get tickets with your seat number on them. After taking the tickets, you need to stand in line to get inside the theater. Now think, no matter where you choose to stand in line, your seat inside the theater is not going to change. Also, your position in line is going to shift each time someone enters the theater. This is a perfect example of time shift property. The theater represents the Fourier transform and the waiting line represents your time shifting. Just because you shift in line is not going to change your position inside the theater. The same way, the time shifting of a signal is not going to change the frequency of the signal or its equivalent Fourier transform. So when you shift signal in time, you are not changing its number of cycles or frequency, as seen in the example. Time shifting don't change frequency. Yes, we will see the mathematical proof for what is time shifting and how time shifting don't change frequency. Let's begin.
Yes, let's get rolling.
If a signal is moved along the x-axis in its entirety, then that signal is said to be a time-shifted signal. Now, a signal can be shifted to either the right side or the left side of the horizontal x-axis. Moving the shift signal to the right is denoted by x of t minus 10, as shown in this example. The use of the negative sign in x of t minus 10 is considered since substituting the value of the new t, which is 10 and 20, always gives back your original unshifted signal. Similarly, time shifting to left is considered as x of t plus 10. It moves the signal to the left and also the original signal, which is unshifted signal, can be retrieved by substituting the new initial and final value of the position signals in x of t plus 10, as shown here. Now let's mathematically prove time shifting. The Fourier transform of x of n and x of n minus 10 is given here. Note, the green highlight is for showing the difference between equations. The first substitution work on this derivation is the base change from n to n minus 10 as shown in the third equation. The next substitution is n minus 10 equal to p as shown here. Now after rearranging and applying the FT formula, we get the time shifting Fourier transform as using w is equal to complex exponential for simplicity of representation, you get the final time shifted Fourier transform as shown here. This time shifted Fourier transform can be generalized for any shift position either to the right or to the left by the final equation. Now let's see how the Fourier transform of the time-shifted signal looks graphically. For a normal periodic sinusoid or a sine signal, we have Fourier transform, which is normally a peak at the signal's fundamental frequency. For time-shifted signal, the Fourier transform is still the same, as the time shifting don't change the number of cycles per second or the frequency of your periodic signal as shown here. In this video animation, we see that the FT peaks at position 5 as the sinusoid in consideration is having 5 cycles between 0 to 1, making the fundamental frequency of the sinusoid as 5.
What about non-periodic signals?
I am glad you asked. Non-periodic signals don't have a single frequency, but they can have a periodic Fourier transform if the signal duration is shorter than the total length of the signal. The periodic Fourier transform also remains unaltered by the time-shifting property, as the starting point and the ending point of the signal is moved uniformly across the x-axis.
What if the starting point and the ending point don't change?
Okay, let's see that example also. As the non-periodic signal gets condensed or compact, the secondary harmonics tend to disappear as shown here. This is because the compact signals represent the sine or sinusoids more closely.
Why and when the harmonics are produced?
It is not an easy question, it is for another class, but let's see something about harmonics here. Secondary harmonics are produced when we have what we call as jump discontinuity, that is sudden high to low. In this case, we have a square signal which is having a sharp or jump discontinuity leading to harmonics in its Fourier transform. The second reason for harmonics is approximation of a square signal from a sine wave. So a sine wave can be approximated to give a square signal through clipping, and clipping produces harmonics. Then there is a Gibbs effect, which is entirely for another class lecture. Now let's come to the last topic for today's class, which is magnitude of complex exponential. This is very important because the magnitude of the complex exponential, regardless of its argument, it's gonna be always 1. Since we have the formula of cos square theta plus sin square theta is 1, the magnitude of the complex exponential is always going to give you cos square plus sin square, and it's going to be 1, as shown here. The FT magnitude always, the Fourier transform magnitude always gets rid of the shift complex exponential, since its magnitude is always 1 and thereby stays unaltered. Thank you for today.
Thank you, Math Qube. You are the best.